Artificial intelligence and machine learning has been the talk of the decade. All right, just making sure, am I audible? Can someone in the audience please confirm?
Yes, we can hear you.
All right, thanks. Artificial intelligence and machine learning has been the talk of the decade. With the potential of artificial intelligence to bring about innovative technological developments, the vision of the future of our world as we know it has drastically transformed. And this vision brings about not only some very exciting possibilities, but also some very valid concerns about user privacy. Today's talk about federated learning attempts to address just that, but also much more on how it can become the foundation of next generation machine learning. Welcome, ladies and gentlemen. This is Sahil Asif, and on behalf of GCU-ACM student chapter, I welcome you all to this virtual technical talk titled Federated Learning in AI and Machine Learning. Let me introduce our guest speaker for today's talk, Dr. Adnan Masood. Dr. Adnan is the UST Global Chief Architect for AI and Machine Learning. He's also a veteran with over 20 years of global experience in financial technology and developing large-scale systems. He is recognized as Microsoft Regional Director and Most Valuable Professional for Artificial Intelligence by Microsoft for his outstanding contributions in the field. As Chief Architect of AI and Machine Learning at UST Global, Dr. Masood collaborates with Stanford Artificial Intelligence Lab and MIT CSAIL, and leads a team of data scientists and engineers building artificial intelligence solutions. Throughout his career, Dr. Masood has been a trusted advisor to the C-suite, from Fortune 500 companies to startups. He's an author of Amazon bestseller Functional Programming with F#. Furthermore, Dr. Adnan teaches data science at Park University and has taught Windows WCF courses at University of California, San Diego. Now, before we formally begin the talk, I would like to thank the Honorable Vice Chancellor of GCU Lahore, Professor Dr. Asghar Zaidi, who is the host of today's talk and will be joining us shortly. Now, without further delay, let me please welcome Dr. Adnan Masood.
Assalamu alaikum. I hope I'm audible. Everybody can hear me. Okay.
Yes, sir, we can hear you.
Excellent. Great. I'm going to start sharing my screen soon. So thank you very much for the kind introduction. That was great. I'm going to start sharing my screen in a second. Give me one moment. Okay, can you see the big screen?
Yes, sir, we can see that.
Okay, I'll move the screen forward. What do you see?
Yeah, it's moving forward. I see your picture with your introduction.
Okay.
And
wonderful. And you are seeing the main screen, right?
Yep, exactly.
Okay, great. Thank you for the kind introduction. My name is Adnan Masood. I run the AI and machine learning at UST. I'm also a Microsoft Regional Director for Artificial Intelligence and Microsoft MVP for AI. Really glad to be a part of this discussion. I hope you will enjoy this. I hope it's not going to be boring. It's going to be more exciting for you because it's all related to artificial intelligence, machine learning. The way I'll do is I'll talk about what federated learning is, what it does, what are the capabilities. I'm not going to just read through the slides. I'll give you some examples and I'll give you some code samples as well, where we'll talk more about like how it actually manifests itself in the real world. What are the real world examples for some of the federated learning? And what are the other technologies which are used in this space, especially around privacy preserving? So if you have any questions, please feel free to stop me. You can ask the question towards the end. I think I have like about 90 minutes. So we will go about an hour to just talk about this, and I'll show you the code samples as well. And then from there, we'll take some time to talk about, you know, if you have any questions, outstanding things, we will discuss that. Okay, sounds like a plan.
It sounds perfect, Professor.
Okay, great. First of all, thank you very much, GCU-ACM chapter, for inviting me, and also for your Honorable Vice Chancellor to be a part of this discussion. Thanks a lot for hosting this. I think this is a great initiative from you guys, trying to get speakers who have experience in the industry and academia to be able to talk to students and share our insights with you guys. So it's a great initiative, and I really think it's very valuable for students to hear from us. Like I gave my introduction earlier, I run the AI machine learning chapter, but I also collaborate with MIT and Stanford University around this area. So it gives me both an intersection of academia and industry, try to get into the understanding of both how academia builds these algorithms and how we can implement that with our customers. So my information, I'll give you the email address and everything towards the end. So if you have any questions, comments, concerns, you can reach out to me. So today what we are planning to talk about is about federated learning in artificial intelligence and machine learning, which allows us to be able to communicate over the span of multiple different devices on edge devices, as well as the devices on the server, to be able to communicate that and train and have the shared prediction model without having all the data aggregated across and put it on one place, right? So the key message, if you can take from here, is the machine learning gets the distributed machine learning with privacy gets enabled by federated learning. So that is one of the powerful thing about federated learning, is that it allows you to be able to do a distributed approach for machine learning without having the data sets aggregated and kept in one place. And the reason for that is privacy, as well as data governance and lineage and provenance. There's a bunch of different reasons. We'll talk about each one of those. But if you want to take one message from this, the idea is that you can do this distributed learning without having to have data in one centralized place. Okay, so there's a slight disclaimer here. Some of the slides I'm going to be using are from these different companies, and they're used as a fair use. This is a volunteer talk. There's nothing being used over here, which is for commercial purposes, and most of the slides are already being attributed here for the things I'm going to be using. So here is the main crux of this presentation. So what are the confidential computing technologies? What are the tools out there? What are the privacy enhancing techniques in AI and machine learning? So all of you probably have an idea of what artificial intelligence is or machine learning is, how algorithms learn. In a nutshell, in a machine learning, you take a data set, you make your algorithm get trained on that data set, that makes a model, and that model predicts different kind of values. So you have different type of model development approaches. You have unsupervised learning, you have supervised learning, you have reinforcement learning, and multiple different technologies are used to be able to build these models, right? You have different algorithms, you have XGBoost, you have random forest, you have simpler linear regression, then you have neural nets and neural networks, you have convolution neural networks, you have RNN, you have LSTMs, you have transformers, you have all variety of different algorithms and models available for training your machine learning models. However, all of these rely and depend on data sets, right? You have to have data sets to be able to train these models. When these data sets are shared, there are challenges when you're sharing this information. And in order to overcome those challenges, in order to not share the data, which has some privacy guarantees, these are the privacy enhancing techniques which are used to prevent data from being leaked, prevent information from being shared. I'll give you an example. So for example, if you have a data set and there's a zip code, and then in that specific zip code or postal code, there's a leukemia patient who lives, and you have to share his or her information with the authorities without having to give away their private information. How would you share that information? And how would you aggregate and then provide that information over to a researcher without disclosing their privately identified information? That's the key here, not disclosing your privately identifiable information. And that's where the privacy enhancing techniques comes into play. So as you can see on the screen, there are 5 key technologies, and these are not just limited to that. There's a few other technologies as well, but this is kind of, you can think of that as the major technologies, 5 different ways of how you can prevent, 6 different ways of how you can prevent things from happening. So one of them is homomorphic encryption. So I'm sure you guys have heard of homomorphic encryption, but it's think of it as a form of encryption which permits users to perform computations on its encrypted data without first decrypting it. So you don't have to decrypt the data. You can operate on encrypted data without decrypting it. It's kind of a trip. You'll be like, so how am I operating on this encrypted information? And that's the thing which HE or homomorphic encryption enables. You can take a data set encrypted and then perform computations. You can perform machine learning operations on that without having to decrypt it. That's not necessarily the talk of this discussion. We can have a whole session on how homomorphic encryption works, but that's a crux of what homomorphic encryption does. The second one is the TEE, or trusted execution environment. Or the trusted execution environment is think of it as a secure area within your processor, where it guarantees the code and the data load inside. So if it's protected from respect to confidentiality and integrity. So your systems are confidential and encrypted. They are kept in what think of an enclave. So enclave is think of it as a region where nobody can mess with that area. So it's a protected area. It is confidential and integrity is kept in place, and that's where you have your code executing, right? So that's your trusted execution environment, as you can see on the screen over here. The third one is a secure multi-party computation, SMPC. Secure multi-party computation, or some people just call it multi-party computation, is a cryptographic protocol. So the way it works, it distributes your computation across multiple parties, where no individual party can see the other party's data. So it's a multi-party computation. So by definition, you have multiple parties in there. But in this case, no individual party can access somebody else's data. However, the computation actually happens on multiple different parties. Like I said, this is again not a topic of today's discussion, but I want you guys to be aware of what are the different confidential computing technologies that are out there. So you are familiar that federated learning is not just the only tool you have. You have a bunch of other things available as well. There's also differential privacy, as you can see on the screen over here. That's a talk of the town right now. It's a rigorous mathematical definition of privacy. So it actually ensures that your data is secure with mathematical guarantees. So differential privacy has very strong guarantees, and it's computationally, of course, intense. But think of it as simplest setting. An algorithm can analyze a data set and compute statistics on top of it. So it can compute different type of like statistics like mean, variance, median, mode, all the aggregates. And that algorithm, it's differentially private if you look at the output, and then you can't tell what individual data was included in the original data set. So the computation will happen, but you won't be able to say what individual was included in that because of the privacy guarantees. So there's a notion of epsilon in here. The epsilon actually adds noise to this data set, and this way you don't have the behavior of the algorithm doesn't change with a single individual is added or removed. So if you have one specific person with a rare disease in a specific area, or somebody with a rare data, so rare is like very special data set available somewhere, differential privacy will ensure that you don't disclose that individual's information as part of this guarantee. Okay, so differential privacy is a really important technology when it comes to confidential computing. It's used a lot in machine learning, especially when you are working with protected data sets and protected attributes and protected industries. So for example, if you're working with healthcare, or if you're working with financial institutions, or you're working with government, it really helps to be able to protect that data set by having differential privacy guarantees. Of course, differential privacy doesn't come for free. You have to have a lot of specific things when it comes to differential privacy in terms of computational cost, in terms of noise which you add. There are some performance issues, as well as some issues associated with the accuracy, precision, and recall. The problem with that is, of course, when you are taking the data sets and then using the aggregates, the more data you have, the better the performance would be as compared to the smaller data sets. So differential privacy really works well when you have a large amount of data set. Okay. And the last one from this perspective is synthetic data. So you must have heard of synthetic data generation. It's a rapidly emerging field when we have privacy enhancing technologies. It's a practical, pragmatic, privacy-enhancing technologies where you're sharing data for secondary purposes. So, for example, if you're generating non-identifiable data sets, so IID or identifiable information is removed from there and can be used to and disclosed without the legislative needs for the consent for the data set. So typically, whenever you are sharing a data set about an individual, there is a need for actually getting the consent from the individual to get that. So if you don't have the consent, you can't really share that information with other providers or with a part of your organization. How do you get around this? The way to get around that is by having a synthetic data set, which has the same distribution, which follows the same distribution as you would have in general for the actual data set. So even though it has a similar statistical distribution, it actually does not have the actual information about the users. So it's a trippy to follow the idea how it's different than the actual data set. So it will have information about the users, which are similar to the users in a statistical term, but not the actual users. So that's why it's synthetic. And that information will not be personal information, so it can get shared across multiple different partners. So that is the synthetic data part. So our focus today is the last one here, the sixth one, federated learning, which is a machine learning technique that trains on algorithms across multiple decentralized edge devices. So like I talked about earlier, you can have multiple edge devices or servers which has local data samples without actually exchanging the information away from one device and then taking it over, but rather you actually get aggregated information. We'll do a deep dive into it. So these are the 6 key confidential computing technologies. If you can take one thing from this whole talk today, is that these are the crux of your privacy preserving machine learning technologies. Homomorphic encryption, trusted execution environment, multi-party computation, differential privacy, synthetic data generation, and federated learning. Today, we are going to focus on the 6th one, which is federated learning, but all of them gets used. Another important point to remember is that these technologies can be used in conjunction with each other. They are not mutually exclusive. They are not used either or. So you cannot say that, oh, I'm going to use federated learning with no synthetic data. It doesn't make sense to use synthetic data in federated learning, but you can do differential privacy with federated learning. That will improve your privacy guarantees. You can use homomorphic encryption with something else. So there are multiple different techniques which can combine together and work together, but they are not necessarily mutually exclusive. I hope that makes sense. So as we move forward, are there any questions, comments, concerns at this point? Yeah, no.
I believe we have none so far, sir.
We are all good?
Yeah, we are good.
Okay,
I
great.
guess
I'm sorry, go ahead. Okay, great. So I'll just keep going. So what are the privacy enhancing techniques? So privacy enhancing techniques are democratization of data. So you will see in this case, machine learning models and insight, which comes as a part of this ecosystem. So these are the some of the classical privacy preserving techniques we are talking about in terms of security, secure enclaves, or enclaves using differential privacy cryptography methods such as homomorphic encryption or group-based anomaly. This is another taxonomy of privacy enhancing techniques, where we are talking in terms of why we need privacy enhancing techniques. So in a real world environment, so you will see that you have a customer, you have a corresponding company, and then you have a regulator. And regulator has certain requirements. So when you're doing democratization of data or sharing data across multiple enterprises, your machine learning models, your insights across the entire ecosystem, the participants will try to create substantial value using that. That is the whole idea of data sharing. When you're sharing data with multiple companies, you have to be able to create some sort of business value. So a balance between the sharing of data across the participants, so you're sharing the data with multiple participants, and ensuring that there's a compliance for the data security and the privacy laws. That balance has to be kept. It's a fine balance, and it's implemented by multiple different regulations. You must have heard of GDPR in Europe. That's a major regulation over there. So anything which you build for a European market has to be following GDPR as a standard. In California, there's CCPA. We have a lot of other privacy guarantees here in the United States, which require you to implement the regulations. So Australia has some privacy regulations, strong privacy regulation. So overall, in the international markets, you will see whenever you're building solutions, there are privacy guarantees and laws by regulators and auditors to be able to put in place. And privacy enhancing techniques, PETs, are approached towards how you can prevent the data from getting leaked. Right? These techniques, like I said, has been around for a while, but applying them on a data-hungry machine learning world where there's a lot of data, it requires some significant amount of effort and thinking ahead of time. So one of the things is you should remember as a developer, as an AI machine learning person, a computer scientist, as a data scientist, that you cannot sprinkle the privacy after the fact. You can't go ahead and then say, oh, I will do it later on, but you have to build it as a part of your ecosystem. It has to be privacy and security by design. So models can be built, machine learning models can be built and deployed without disclosing the actual data. That's a key point, that you don't have to disclose the data. You can build a model, you can publish a model, you can have a model, but you don't have to build it in a way that it discloses or outputs the original data or causes data leakage. And that's where these privacy preserving techniques come into play. Now, since the focus we have today is federated learning, these are some of the key attributes you are seeing on the screen right now. Federated learning makes it possible for us to be able to build these machine learning systems without direct access to the training data. What does that mean? So I'll give you a simple example. All of you have phones in your pockets, correct? Like you have my phone over here. I have another phone over here. So all these phones have their own implementation of differential privacy. So for example, if an iPhone, you have been implementing differential privacy for a very long time. The way it works is this phone will actually host a model of its own. And that model resides on this edge device. So phone is an edge device, it lives on the edge, and it will host a model of my audio. So when I say something to it, my audio model gets stored and it understands when I say with an accent, the way my voice sounds, the way I pronounce different words. It has a local model based on my accent and my other information. So each one of you have a phone, and those phones would have their own localized models. But the data doesn't have to be necessarily shared with a server. So it doesn't have to go to Google or Apple or Microsoft or Facebook, but rather it can live locally on the phone itself. The aggregate information about this data goes to the server. So the data aggregates, goes to the server, and then train the larger model without disclosing your actual original local model. And that is the essence of how federated learning works. The data remains in its original location, which helps to ensure privacy. It reduces your network communication cost. And in this way, your edge device computing resources are used. So instead of all the calculations, all the mathematical calculations for building the model, does not have to run on the server. It's running on my phone. But my phone has a lot of computational power. Your phone has a lot of computational power. So why not use it? In order and you can use it and learn the model on the edge device. And one of the principle of data minimization is established by the GDPR is that the smart sensors take this advantage of federated learning, and it makes it compliance friendly, as well as you can utilize your computational power which exists locally, right? It's a great fit for smartphones. It is a great fit for consumer IoT, healthcare, and other privacy sensitive instruments where you are in an industry where you're applying it. So you don't have to share all the data about this. So in some of the examples I'm showing on the screen over here, if you have a community hospital or a medical research center or a cancer treatment center, But all of these have private data, and you don't have to share the local model across with the federated server directly. They will build a global model based on the privacy preserving guarantees with aggregated models, which are created using the local models. However, the local models doesn't actually get shared. So how does this magic actually happen? Right? You were wondering like, how is that possible that you can take information from a local model and train a global model, but without disclosing information about the global model? So this is the algorithm of federated averaging. It shows you how it is done, right? So federated optimization data is not on IID, it's not identifiable. And it's unbalanced across different clients, it's massively distributed, and it's communication restrained. So these are the four main properties on this case, which means you don't have to share the entire data set over there. And if you will see this algorithm, I recommend you to look at the paper. It's called Communication Efficient Learning of Deep Networks from Decentralized Data. I have all the references for these papers towards the end, and I'll show you some of the things you can work on as a student if you want to contribute in this area and how you can work on this area. So you have a number of clients. You look at the algorithm over here. There are K clients. They're indexed by K. B is your local mini batch size. Mini batch is the one which gets transferred over the batch, and E is the number of local epochs. And then you have the learning rate. So the server executes each one of these nodes which are available locally. So you see it's actually getting in this for loop, it's essentially getting all this information, but it get the client update. You see this client update, and client update is a separate function over here that is running on the clients for the local number of epochs over here. So you have the local epochs which are running and performing operations to get this information back from your server, and the server actually gets the associated weight. You see the return the W to the server, that's the associated weights you get back. And these weights become a part of your server execution as it runs in parallel to get the client update. And you get this weight of T plus I as a summation, which becomes a part of your client update as an information. Comes back from the client. So it's running in parallel, which means it does not require all of the clients to be able to respond. And it's also robust, which means if a client doesn't respond in a timely manner, it can still move forward and learn from the other clients. So essentially, you can say that federated averaging here, as you can see, the algorithm itself is communication efficient because it's running in parallel, and it doesn't require the client update to actually happen all the time, because if you see, submission itself is a robust approach where a client can keep their data locally for privacy protection, but a central parameter server, which is here, is used to communicate between multiple clients. A central server distributes the parameter to each client and collects the updated parameters from the client. So here it's updating, collecting all the updated parameters from different clients, right? So in this case, you can see that all the data which is being made available for different sources into the centralized data, you can have a data lake or you can have a warehouse where machine learning models are being built, right? So the data moves from different sources across different systems and different environments. It could be an iPhone, it could be an Android, it could be an edge device, which is running like a Raspberry Pi. But data resides where it is generated, which means on a phone or an edge device. And the models are individually getting trained, and the source of the data generation and models are sent to the centralized server. So this is a centralized server. The difference that the data doesn't want to move from one location to another, the model is moved to the federated learning. So if you look at the algorithm here, you don't share essentially the data, but the aggregate data, and the model gets moved over there. So Google started using it a lot, and you will see some of the examples in this case where the sharing the data across multiple networks can be risky, and therefore you need to have a way of aggregating information like this. For example, if you have private information like X-ray or CT scan or other things, you can take the information, create this centralized model server, and this enriched model can then be used by another hospital. So for example, if you have a bunch of X-rays, a bunch of CT scans, the aggregate model gets trained, and then it can be used by somebody else where the privacy of the patient is secure. However, you don't have to necessarily share that. So I'll give you a couple more examples of how it works, but this is the underlying algorithm, and you can read more about it in the reference paper as we move forward. So in federated learning, some of the places where it gets used. So you will be wondering, like, what are the key places where it gets used? One of them, of course, is the predictive maintenance on IoT devices. So if you have IoT devices, they are highly useful with federated learning. The main idea is to train the machine learning model to transfer the data to the cloud server. The same with IoT, you don't have to transfer it. Smartphones is another way, and healthcare devices, you can use that. Enterprise applications are a great use case for federated learning. Now, some of the key characteristics: the performance improves with more data. Now, performance can improve with more data in general. In machine learning, that's one of the key attributes. The more data you throw at this, and the more information you generate. But models can also be meaningfully combined. You can train models. You don't only have to predict, but you also can train models. And a use case, if somebody asks you tomorrow, you join a company and your manager is saying, why do we need federated learning? And you can explain to him that if you need privacy, or if you have power consumption issues where you can't transfer the data over at all times, if there's a high cost of data transfer in this case, in your case, or your model needs to get improved in more data, then it makes a really good case for you to start using federated learning. And federated learning makes sense for in these use cases. Now, let's talk a little bit about what are the characteristics, features of federated learning are. So federated learning, like I said, it makes it possible for you to build machine learning system without direct access to the training data. The data is remaining at its original location, which is going to help you to ensure privacy. It reduces the communication load cost, and it also uses the computational power of the edge devices, right? So the principle of this data minimization is established by one of the regulations around GDPR, and then you can use that. So data locality and distribution is massively decentralized, and it actually gives you a non-NIID partition. Data is siloed in the sense that it actually helps you with a small number of coordinating entities. Now, data availability has limited availability and time of day variation. So which means you don't have data available all the time, but it's available some time of the day or other times of the day, right? So the ones in the bold, remember, those are the right ones. The ones which are not bold are not correct. So remember that this thing I'm showing on the screen, the bold ones are the attributes of federated learning. The rest are traditional distributed learning. So somebody may ask in the audience, might be wondering, like, oh, so what's the difference between federated learning and traditional distributed learning? So these are the differences between your traditional learning and your federated learning. In distributed learning, you have data available all the time, almost, right? But in in federated learning, you have limited availability of this data, time of the data variation. In case of federated learning, you have a statelessness. In case of distributed learning, they are stateful. In terms of reliability, distributed learning, we assume it's reliable, the nodes are available. In case of node reliability, when it comes to federated learning, we consider it as unreliable. But these are some of the differences between your traditional federated learning and distributed learning. It could be a little bit confusing because some of these are bold and some of these are not, but I want to make sure that you are familiar with what's happening over here, okay? All right, so here's an example. We will give you a quick example over here around how nodes learn and how the information goes from your different nodes and the federated learning. You will transfer this data over. So let's take a look. You have a network of nodes, right? So you have a bunch of different nodes, and the server is taking data from these nodes, and nodes are sharing the models rather than the training data with the server. So step one, you have a server which has an untrained model. If you see on the top left, this is a server which has an untrained model. You have a bunch of different nodes. Now it sends a copy of the model to the nodes. So you now have a model here, a TensorFlow model, a PyTorch model, or any of those models, and it sends that model over to each one of these individual nodes. Now, here you'll see the nodes now also have an untrained model. So model came from server and is now residing on these different nodes here. And these nodes are now going to get individually trained. So you'll see here these nodes. So you see these dotted information is this data which gets from here from the specific node, and it's learning, and nothing is getting transferred over to the server because it has given the model down there. Now, each node is going to try to get this model fit, which means it's it's learning from it and fitting that model and trying to understand what's happening there. Then each node sends a copy of its trained model back to the server. So remember, we are not sharing the data, we are only sharing the model. It goes over to the trained server. The server now learns and makes an average of the model and try to learn from that. So it will have an average of the model where it doesn't have all the information about the model from individual data sources, but an average of that. So we repeat the whole process many times. It keeps repeating over, and the server now has a model which captures the pattern which is happening on individual nodes, and those nodes become a part of your training data. And keep sending the information over there. But at no point each node share the training data with each other, and it has privacy. So not one phone doesn't know information about another phone. One medical device doesn't know information about another medical device. And the server doesn't know all the information about each one of these nodes, but rather it has a model which captures the pattern of each one of those nodes in aggregate, but not the individual data. Okay, so that is what federated learning is all about. So I've given you a couple of examples. I've shown you the algorithm. By now, it should be very clear what federated learning is and what it does and how it is secure and private and why it is so important. I'll take a quick pause. Any questions, comments, or concerns at this point?
Okay, so what you talk about that non-IID data? What is that non-IID data?
That's a very good question. So individually identifiable data. What is your individual identifiable data? So for example, your SSN, your date of birth, your anything which can individually identify somebody, that's IID data sets. So if you have information about you which you don't want to get disclosed due to regulations, due to your personal privacy reasons, that's the IID data which you don't want to get distributed across multiple different platforms. You don't want anything which can individually identify you. Does it answer your question?
On each machine that contribute in federated learning, the data distribution could be different. So how does the server machine handle these different kind of data distributions?
The data distribution could be different. Well, I don't know if that's essentially true in the sense. So let's talk about models. I'll give you a couple of examples here as we move forward in use of federated learning, and you will see that the distribution, even though individually they are different, the aggregate, the reason why we keep the models locally is to accommodate that local individuality. And then the aggregate, when it goes online on the server, that shares the shared attributes across all of the things. So your individual identity stays with you as a local node, but the aggregate information across goes to the server because that's shared across with a bunch of different nodes. So here's a good example. You guys may have a Pixel phone, so Google uses a lot in this. So I carry both. I have a Google Pixel phone, and I also have an iPhone. Pixel phone does federated learning, so does iPhone, and Google learns from both. The way I type, the way I uh, say different kind of words, the way I have my shortcuts, etc. So for example, here you're using Google keyboard, and the keyboard can predict what are you going to type. Most of you have this feature when before you start typing, it starts typing for you. In Apple phones, the autocorrect is not the best, but with Gboard or with Google phones, it's much more accurate and better, and it's much more customized to your individual needs. How does Google know your local model, like what I'm going to type based on the phone based on my own predictions. So there are certain words I type which it knows ahead of time what I'm going to type, which nobody else will use. So for example, if you have certain contacts in your address book and you're typing their name or you're speaking their name, Google will pick it up and it will be able to type it up for you. And the other person definitely doesn't use those acronyms or doesn't use those names. And they won't have the same capability. They will have their own capability. For example, if my son's name is Ali and I'll say text Ali to ask him to do something, it's going to know that Ali is ALI and not Ali, like ALLIE. Somebody else, and for example, in the United States, Ali is a more common name, and it's a girl's name, Ali. But it would not type Ali, it will use Ali because that's curated and customized model to my phone. So the models are trained locally based on your own preferences, based on your own predictions. So there are certain things here, emoji prediction, action prediction, etc. When I wake up at 5 a.m., the first thing my phone tells me is to turn off my Alexa alarm, and it will just put it up there, the first thing as a prediction. So these predictions, and nobody else will get that prediction because Alexa is something which is local for me. It's running on my in my home and my devices which I use as part of my smart home ecosystem. So what I'm trying to say is that the federated model allows you to keep your local models local. So IID information and anything which is specific to you are local. Even the emojis, the kind of emojis you are going to use, the kind of actions you are going to use, the kind of keywords you are going to use, they are kept local. So however, there are general use cases, the commands you give to your phone. Tell me about something, about a map or something associated with a world which becomes a lot of people are using. So for example, if you say, tell me a joke, hundreds of other people are asking the same thing from Google's, from Siri, and that becomes a part of an aggregate model because that can get transferred over to the server. And then now Google knows that a lot of people are asking Siri and Google about weather, about how's the weather, how's the, okay, Google, what's the weather right now? So these are the kind of things which a model can learn as an aggregate instead of using it as a local, because this is something which is a lot of people use it becomes a part of the federated model in the cloud. I hope that makes sense, the difference between your IID protocol as well as your general localized protocols in this case. So since we have made that clear, hopefully it makes sense to you. Guys, what is the individual identifiable information kept on the local nodes versus what is kept on the server? What are the open research areas? What are the things you can do right now with the servers? With the federated learning in research or in development. Some of the things I've listed over here, there are other areas as well, including building and development of libraries. We'll talk about libraries in a second. But building optimization algorithms for federated learning is an important area because communication efficient algorithms which have more tolerance for offline nodes, they can work with this with non-NIID data. That's an important area. Scalability of federated learning to larger models, because it is very expensive to do training, especially having precision, accuracy, recall, and other attributes available for federated learning without having to work with it with larger models. With the smaller models, it works better. With larger models, the performance deteriorate. So you'll have to have that available. Novel applications of federated learning, the theory of federated learning, enhancing the security and privacy, combining multiple different federated learning approaches together, a bias and fairness in federated learning settings, attacks, robustness, adversarial attacks, poisoning of the models. These are area of research. Not everyone has to have the same model. Multitasking, pluralistic training, personalization, domain adaptation, generative model, transfer learning, semi-supervised learning, how all these different type of learning algorithms work with federated learning. Because you realize when I talked about in the beginning, you can use supervised learning, unsupervised learning, reinforcement learning, all of those as part of your federated learning approach. Federated learning does not stop you from using one or the other. It allows you to be able to combine multiple different techniques together. Federated learning is a security and a privacy preserving technique. It's not a machine learning algorithm. It's not an algorithm for training itself. It's an algorithm to be able to keep your data secure and private. That's the guarantee it provides. It doesn't provide you the guarantees for training. So secure, of course, when I said data secure, it's not necessarily a security algorithm. It's not a cryptography algorithm, but it's secure in the sense of privacy. It gives you those guarantees. Okay. So these are some of the open research areas for you students. If you are interested in working any of those, feel free to shoot me an email. I'd love to discuss more with you as you move forward with your undergrad or grad degrees. These are really important areas for you to work on. Okay, so we have spoken about what are the different open areas. How much time do I have left?
So approximately 45 minutes. We're halfway through the time.
Great. So I think we have good time now. We'll talk about the libraries and I'll show you some demos. Okay. If there are questions, feel free to ask me questions in the chat.
Yes, Doctor, I have few questions. What I'm assuming is that federated learning is basically based on a simple assumption that all participants of the federation are honest and they can participate honestly in the federation. But this federation learning, I have not understood that it is not restricting the participants to be honest. It is just assuming that they are honest. So if some of the parties are trying to cheat the system or trying to cheat the model by faking the inputs, how federated learning systems then can defend themselves from these malicious kind of inputs?
So Ali Raza was asking this question. It's a wonderful question about adversarial learning. So there's a whole area in machine learning around adversarial learning and how you address with inputs which can be poisoning the model itself. So model poisoning, adversarial attack on model, figuring out the data sets which are outliers, so inputs which are outliers or anomalies which are used to defy the quorum. So there's a quorum-based learning, and then if some entities come in and then they try to poison the data set and try to give this information, which can make your model drift or decay, that's a problem. So what you're talking about is a larger problem in machine learning, where you have information coming in from multiple resources, especially if you're using online training or active training or batch training. In either case, you're getting data from parties which are non-trustworthy. How that works. So trust in machine learning or federated learning ecosystems is a very well studied area where you are looking for distribution which are coming in for different data set, and if the distributions are outliers. So outlier detection, as in if everybody is saying that my salary is 100K, and all of a sudden somebody starts pushing in outliers. So somebody keeps saying my salary is $500,000 and my salary is $1 million, and somebody starts putting data sets with information, try to change the data distribution. Libraries such as the ones I'm showing you on the screen, the TensorFlow, the FedEx, the Flower, the federated learning libraries, they all have modules to detect outliers and identify outliers and discard outliers. So secure learning is typically depends on the control on both ends, but as a client and the server. But if you have outliers in there, information being sent, it will stop it from processing those outliers. In our case, for example, when you're working with medical devices or you're working with cell phones, both the client as well as the server is controlled by the same party. So Google is controlling the input which is coming from the client. So it makes sure that whenever the input comes from Gboard or other things, it's all controlled from the local device. It doesn't get the federation doesn't get corrupt because somebody has a phone which is causing which has outliers, or it's trying to ingest some data which doesn't belong to the same distribution. So it will control that. So it already filters out any kind of outliers from local, but it doesn't mean that these attacks can't happen. These attacks do happen, federated attacks, and you can probably have read about some of the attacks, like people being able to get a lot of cell phones in a cart and try to produce a traffic jam. You must have heard of that, right? So people, somebody has put everything in the cart, and then all the cell phones in the cart with the Google Maps, and then try to simulate that there's a traffic jam, and the Google Maps get that information, and they get all like it starts showing that area being red. But that's few and far between. Whenever you have an ecosystem, when you are relying on clients to be able to provide this information, there is a chance of foul play in this area, and quorum-based computing discusses that. So if you look at the quorums for example, blockchain, there's also a 5150 attack, right? So you have 51% of the quorum members, if they try to attack it and try to diverge from that, that can cause these problems. So great question, by the way. It definitely it's a challenge, but since the client and server both are being handled by the same party and outliers are discarded, there's a very little chance of this happening. In this case for federated learning. However, whenever you are building a federated learning system, you have to look for the distributions and make sure that all the information which is getting in your system is checked against outliers and anomalies, and not necessarily getting, you're not aggregating those anomalies, otherwise your data will be only as good as the outliers themselves. So I hope that answers your question, Ali.
Thank you. I got that. There's another thing which I got picked from your earlier discussion. Please correct me if I am wrong. The point is that in order to handle the diversity in the data, I assume you said something like that differential privacy will require to include some noise in the data. So in such cases, how federated learning can guarantee utility of data if there is so much noise considering the diversity of the data?
So this is the question. I'll just repeat the question so to ensure that everybody gets it and my understanding is correct. This is the problem which Ali is talking about is more around how the utility of data and the noise. So epsilon is a factor which you use. The more noise there is, the less accurate the data is, or the utility of data would not be there. Which means if you're taking a data set and you're adding a lot of noise to it, then what about the prediction quality? How effective the prediction quality would be? So there is a trade-off. I wouldn't say that it's always going to be perfect. There's a trade-off between the privacy and your security, as well as the model which you are using to predict. So if you want to have rare data hidden, if you don't want the distribution of individuals to be given out, then yes, you have to use that guarantee. So I'll use my original example. If you have a zip code or a postal code, and there's only one patient who has that rare disease and who lives in that area, and you are applying differential privacy, that person will be hidden in the aggregate, or in when you try to find out that patient in any zip codes, you won't be able to find him. Right? That's just, his data would not be there, period. And why? Because there are privacy guarantees. If that data gets included as a part of the differential privacy, then you will be able to find him. And the differential privacy by itself guarantees that you are not able to find that individual. So any distribution you have where 10,000 or less people are there, and then you are able to find that rare event will disclose the individually identifiable information about that that individual, and that's why you don't want to have that data as part of your distribution. So you will be like, hey, but now we are missing that data. So what about that patient? That's a trade-off. You can't have an individual in a specific area who has that information become a part of the aggregate, because then you can get to that person. The differential privacy guarantees that you can't get to an individual or any individually identifiable information. So if I take that information out of the data set, then first of all, you are missing that data, but that is a trade-off you are willing to make in order to keep it secure. Okay, so that's the trade-off in this case. But though, like I showed earlier, the more data grows, then the distribution becomes much more normalized, and in that case, you don't really miss out on that rare event, because that's a rare event by definition, and you have already eliminated the outliers. So your model is trained for the world, not for an individual outlier. I hope that makes sense.
Okay, thank you.
Great. So
when we try to train our model on our mobile machine, do we have different models for every single machine? Like one of the machines will be running on neural network, other one will run like linear regression. Is it possible? And the central server will be running some other model. It becomes some ensemble learning. Is it possible, or all model or all machine will be same?
So the question is regarding the models, if the models are going to be identical across the different devices. Yes, so all the models, as in what type of technology is being used, what kind of parameters are getting trained, those are all identical. So it's not going to be like one of the phones is using a random forest and the other one is using XGBoost and the third one is using something else. That's not how it would work. It will actually have the same model type being distributed across, but the parameters will be different. So your parameters, the weights you have are different than the weights which are trained for somebody else. The hyperparameter tuning might also be different, but in general, the models are all going to be identical because that is the aggregate which your federated learning is aggregating on the server. The server has that model, and that's why you saw earlier I was showing you how in this case you probably have seen, right? The model gets down from the server and those nodes actually share those models, right? So the server ends up sharing the model down. So then it gets trained and then the model goes up. So the model, it stays the same across the nodes, either whether it's a computer vision based model or an audio based model or an NLP model, that will be the identical, but the data is different across different. I hope that makes sense.
Okay, when we train our model on cell phone, do we need to install some application, or what kind of setup there would be?
It's already there. So you have your phone's already learning from your habits based on the device. You don't have to install anything separate. It's already, if you're building your own application for differential privacy, then yes, you will have to. And I'll show you quickly how do we start different agents if that's what you want to do. So these tools like TensorFlow or FedAjax or Flower or Flute or PySift, they have the capability to install and run these agents locally on different machines. But the ones which we are using right now, the frameworks, they already have that built in your system. So Google already has the software installed on your phone, which is doing the learning and then sending the data back and forth. Okay. All right, so let's talk about the data and frameworks over here. Well, we are using this secure data, the libraries and frameworks for secure machine learning. We have to secure these machine learning models, and models are subject to a different type of attacks, such as like ones you were talking about earlier, model inference, member inference attacks, model inversion attacks, model parameter extraction attack, PySift, TensorFlow encrypted, TensorFlow privacy are some of the frameworks here I've listed over there, which will help you securing models. So PySift is one of the popular ones. Which was using PyTorch, and you can also extend it to use TensorFlow and Keras. Keras is just a high-level library for TensorFlow. I'm sure you guys have all heard of TensorFlow. TensorFlow and PyTorch being the two major platforms, and PySift is an extension of. It uses Sift, which was the main library, and then PySift is the Python extension for Sift. You can use it to apply the remote execution. So one of the questions I think Sabdar was asking about what you would do for remote execution, differential privacy, homomorphic encryption, secure multi-party computation. We talked about earlier federated learning. All of these are supported as part of the PySift framework. TF encrypted is a framework here. You will see as part of the TensorFlow. When I put TensorFlow in there, but TF encrypted is the actual framework which integrates your secure multi-party computation and homomorphic encryption, both of them as part of your, if you want to use it as a differential privacy candidate. TF encrypted also offers you a high-level API called TF encrypted Keras. As I said, Keras is the library which gets used as part of TensorFlow, a higher level library. TF encrypted also aims to make your privacy preserving and secure machine learning possible without having expertise in building. So any one of you who wants to build that framework, you can easily use TF encrypted without having to write your own node management system. Rather, you can just use TF encrypted. Another library, TF privacy, it's a very important library which applies your differential privacy techniques So the model doesn't memorize specific training data locally and becomes more generic in nature. So far, all the things you have learned about machine learning is that your data has to be pure. Shouldn't have noise. You can remove outliers. And the things I'm talking about in terms of privacy might be making you like, why is that? Like now I have to use data which has noise in it. But there are certain trade-offs and guarantees you have to do. And all the major machine learning companies, all the FAANG companies, including Netflix and Microsoft and Google, Apple, and Facebook, they're all using differential privacy in one way or another. So therefore, you don't have to worry about the quality of your predictions. It's there. The prediction quality is guaranteed in the sense, along with privacy guarantees, you can have good predictions. So don't worry about that when you are using your privacy guarantees in here, because machine learning algorithms are robust enough to be able to learn even on encrypted data, even with homomorphic encryption, even with differential privacy. And that's a great thing, that you can even do calculation and things on top of your models without having to compromise on the privacy. Okay, so that's the thing. So now I'm going to show you a quick demo. Any questions so far? I will wait till anybody has any questions, comments, concerns to talk about. No, yes, maybe. Okay, I guess we are all good here. So I will go ahead and share my notebook. Okay, I hope you guys can see my notebook. It's a Jupyter notebook here. You all must be familiar with Jupyter notebook, so you can go to colab.research.google.com. So this is the link, colab.research.google.com, and you can create your own notebooks here. Colab is a really great tool for researchers. So colab.research.google.com is where you can make your own notebooks. I'll share the link for these notebooks with ACM chapter, so they can share it with you guys and show it to you. But this is a really good resource, Colab, where you can run Jupyter notebooks on Google for free. And it really helps you being able to learn Python, data science, machine learning, deep learning, all of those things really effective. Okay, so I'm sure most of you are already using Colab, but this is a really great tool. And that's where I'm going to show you one of the libraries I talked about called Flower. Flower is a recent library. Okay, so I'll show you introduction to Flower and how it works. But I'm hoping that since you guys haven't said anything, you can all see my screen here. Okay. So let's just start with this. An introduction to federated learning.
So you can see.
You can see it, great. So we'll talk a little bit about.
Sorry for not confirming earlier.
That's okay. Flower and PyTorch. Some of the tools I've talked about, like PySift and TensorFlow Federated, we can use that for a variety of different things. Flower I really like as a library because it is fairly lightweight and easy to install and easy to work with, and it doesn't have much baggage or from earlier Keras style training. And the reason I say the baggage is because it's not as verbose. It doesn't have as much setup related things which you need to get things going as compared to you will have with other things like if you're using TensorFlow and Keras. I do have another example over here. I'll talk about the simulation with TensorFlow and Keras, but first I want to just show you how you can do federated learning with PyTorch and Flower. Flower being the library. So here I have it set up already where I'm doing the federated learning over this. It's already connected to my GPU runtime. You can see my cats over here. A runtime, you can say the runtime I'm using here is a GPU-driven runtime, and I'm using high RAM. These are things which are available as part of Colab Pro, but if you are just using a regular Colab instance, you can easily just use a regular runtime. Doesn't really have to be a GPU runtime. It's just if you have, I typically use it because if I'm doing GPU-based computation or CUDA, then it helps me be able to run those much more effectively. Okay, so here I go ahead and I'm going to go ahead and install these dependencies. I think I ran this right before this meeting, so these should already be done. It's now installing the simulation the package of your flower. So it's downloading and installing the flower simulation, a specific version of 0.18. You can define the version here, like I'm showing you here, what simulation version is getting used. And so these are essentially just installing the dependencies I need for this libraries, right? So it's just installing all the corresponding wheels and everything. And all right, now in this case, that now all my dependencies have been downloaded and installed. This is just going to check and make sure that I have all the torch devices and everything. I press Control Enter. You can press this, and it shows me that the flower 0.18 is there. This is NumPy. This is torch. This torch vision, and this is training on my CPU and not on my GPU. I can change it to GPU, but since I'm not doing anything specific, it's okay. All right. Now let's load the data set. So you have these classes, plain, cardboard, etc. So I just created a set of these different classes over here. So I'm going to do the training on CIFAR. CIFAR is one of the convolutional neural network data sets where you can train. It's CIFAR is a very popular data set for image recognition. I'm sure you guys have worked on it in the past, where you can use the data set to have classification and learning based on this this data set. So number of clients is how many clients you have. And in the case of differential privacy, a node is a client. So all the clients which are running, each node is a client, and then it gets trained on each one of these clients. So here what I'm going to do next is I define the batch size for learning, and then I'll load the data set. So loading of the data set is happening from this data set table. I have the sample data over here, but it's going to download the CIFAR data set for me and then be able to work from there. Okay, so download and load. So it's going to go ahead and download the training set for me and then being able to extract all this information and work on it. So CIFAR 10, this is the one which is getting the information down from the CIFAR website. So you see here, now I have this data set attribute, data set folder with all the information in there. So as soon as I run this, the CIFAR 10, this constructor went ahead, created a folder called .dataset and downloaded all this information in here. If you are using some traditional methods, traditional libraries, you may have to download this and then store it in your dataset over here, like I'm showing. But in this case, the constructor does everything for me, so I don't have to do it. Most of the modern libraries, including TensorFlow, has these datasets built and as part of your repository, so you can easily use them. But this just shows that the download is true. It gets all this information in it. It will also split your each partition into training and validation sets. So you, as being a machine learning engineer or people who are getting started, remember that any of your data sets have to be split into training and testing. So you typically take 80-20 split or 90-10 split, and you also do this thing called cross-validation. Cross-validation is that when you do the split, maybe the split is not ideal. Maybe when you split it, some part of that actually had some sort of stratification. The stratification means that data set may have an inclination or a distribution which doesn't follow the rest of the data set. These concepts may sound a little foreign to you if you are really new to machine learning, but cross-validation is a very fundamental term in machine learning. So I highly encourage you to go and check out how do you do the splitting of this. This is not really a time or a place to explain that in further detail, but you do this detail, you do this split here, and then here I'm doing the random split to figure out what type of data set for training and validation is going to get used. Then here I'm loading the loaders, which gets the information from your training data set. So this is the data set training goes in there, and then validation loader now has the data set for validation. So in this line, I have assigned training loader, training data set, and validation data set based on the random split. It gives me two of the elements, and they get both populated and then passed on to the loaders. All right. So now this has happened where this whole information has been extracted, and I have created training set and the set for loading. Okay, moving on. So you have 4,500 training examples, 500 validation examples. So we have a 5,000 image data set, and out of that, I've taken 4,500 for training and 500 for validation. All right. Now let's see. So now in this case, now I'm going to show the images. So the training is going to happen in distributed manner, and you will see how the data set is showing you based on the data which is coming through the plane, the cars, the cats, the horse, the ship, etc. And this is the classification. So this is the data for planes. This is a data set for car. You can see in this data set, the accuracy isn't really there. You can see that there's a difference. For example, this is not really a car, it's a truck, but these are this is the initial run. It's just showing you what are different classes available. Okay. Now let's do the centralized training with PyTorch. So we will go ahead and create a model. It's a neural network model. We are creating a convolutional 2D model. Here is your convolutional net. I'm running it. It has created a basic commands for this, and with the neural network module. And now I'm going to do the training. So I'm sorry, not doing the training, but rather running the training model. So these are just the functions for training. I'm not running them. There's a training function right here. It defines you what the loss function looks like, what is optimizer, what are the outputs of that. So this function is being declared over here, then the test function is declared. Now at this point, we'll do the training of the model, right? It's going to run 5 epochs, and then it's going to train your model. So you see here the epoch 1 runs. The validation loss is 0.05 with a 0.272 accuracy. It's pretty fast, especially because it's running on Google servers. And here you can see the accuracy is about 0.394, which is, of course, not the best, right? 40% accuracy means even if you just do a coin toss, that might be even better than that. But in this case, if I increase the number of epochs instead of 5, if I go to 100, it may actually improve the accuracy. Let's try that out. Let's try 10. Let's see how that works. It may take a little bit of time, a longer period, but it will increase the accuracy. For the purpose of this demo, I kept it minimum, but the more epochs you add, the better your accuracy will become. So you see here it is, it's increasing. And that's where your learning rate and your loss function comes into play. How many epochs you want to run. So now you see how the accuracy keeps increasing as you increase the number of epochs. So in this case, maybe about 30 or 40 will get you to a very high accuracy in this case. And the loss function is, as you see, it's getting reduced. Okay, so about 41%, which is not good, but at the same time, it doesn't really matter for the purpose of this tutorial we are going through. Now let's go ahead and try to do training with Flower. So far, you have seen just traditional learning. Now let's do it with Flower. So we get the parameters. I'm defining these methods. You don't need to worry about that. That's just utility methods. Now you're implementing a Flower client. I've created a Flower client class, which takes these parameters for get parameters, fit and evaluate, 2 methods. Fit, as you know, is the function which trains the model. In this case, we have a distributed agent, which is going to train it. So when I talk about distribution, in this case, we are not necessarily creating a real agent. So I don't have like 500 edge devices sitting here or 500 phones sitting here we are going to get trained on, but rather we'll create this virtual client. So this is the client function, which creates a Flower client. Client is the edge device, which is the node. And now I've created an edge strategy where the federated averaging is going to get used. Federated averaging, we talked about earlier. You saw that in the slide. That's the function. So federated averaging takes your fraction evaluation, different tuples. It accepts failures that are callback functions. And this is a strategy which you are passing in there for federated. So if you'll see here, you have a bunch of different strategies available. One of them is federated average. When you have adaptive federated averaging. The other one, which is federated averaging for Android. So you have all these different kind of averaging capabilities available. There's a fault tolerant averaging. These are the different strategies you can use as part of your strategies for that. So now I'm running this strategy. It has instantiated multiple different clients, and now it's training for individual clients. So each client which is running as part of the simulation is training on its own. So it has created number of clients. How many clients were there originally? 10, right? That's what we declared earlier. There are 10 clients getting created, and I think we declared it somewhere around here. Maybe said we will just have where did that go? So this is the number of clients. We declared this literal to be 10, and this is the one. Let me save it. So this is where we declared 10 clients. You can create more clients if you want, and those virtual clients are actually now getting trained. Let's see. So give it a couple of minutes. It's running the simulation on different clients, as you can see here. It get initialized with the different resources which are provided. It initialized a global parameter. It is fitting, sampling with 10 clients out of 10. It has getting all the results with no failures. A strategy sample for 5 clients, a strategy sample for the 10 clients. So it's right now it's running this strategy on multiple clients. It's now training in a distributed manner. So previously you saw how the training was done on one node, which is my server. Now the training is actually getting done on different nodes. And we are going to get the sample data from that, each one of those clients in a federated learning manner. This means individual data is not going to get shared. Only the model, which is trained on these individual clients, are getting shared over to the server for me. So once this runs, I will actually get the corresponding model on my server, which shows that the simulation returns this. So the notebook has really good notes. The flower, it talks about how you have 10 clients and all the available clients are going to return you the information. But Federated Average also knows that all the available clients can get used, which the fraction fit is 1.0, but you can create it 0.9, which means only 9 out of 10 will be available at some time. So you can create and simulate that noise as well. So again, this is simulation, which means I don't have physical clients, but it's actually creating those instances of clients for me, simulating as if I have physical clients. And it does all the real work for you. So here you go. So I got that distributed loss here a bit 0.48. Accuracy for the 5 rounds, because that's how many epochs I was running. And you can see the accuracy and the loss are fairly identical to what we had earlier when it comes to running this with our non-centralized, and when we are doing that. So you see here losses, distributed losses, matrix losses. The time it has taken to get the information out was longer, but here you can see each one of those attributes. I'll zoom in to show you right here. Right, so each one of these losses for individual entities here, like node 1, node 2, node 3, they are different, but they are coming from each one of these specific entity, a specific node. So you don't have a centralized function, but rather it's running separately from different nodes, and that's where the data you're getting from. Okay, so you can run it locally. You can play around with the simulation. I have another notebook over here which is very similar. It shows you how you can create the same thing with TensorFlow. So this is TensorFlow library. You probably are familiar with this syntax, which is a Keras syntax. In this case, we are using PyTorch. This is Keras syntax, and it does something very similar. I'm not going to run this just because it essentially shows a simulation of the client, and you have already seen here how do you simulate the clients by creating it, and how you can create a strategy and do the Fed averaging for that. Try running multiple different type of algorithms here, and then see how you can try to simulate different strategies. There's a tons of great examples available as part of Flower, the library, and also with part of PySept, the library. I didn't show you PySept, I just showed you Flower. It's easy to understand because you don't have to create a bunch of verbose text in there, but I'll share these notebooks with the team so they can see and ask any questions you may have. So before we conclude quickly around this, as the organizations are adopting cloud technologies for data storage, for data analysis, for embedded AI, etc., their business processes are important to ensure that model security is taken care of. And if everyone you work with, any organization, large organization you work with, has to ensure that the model is secure. And with many of the AI applications are moving from your POC, but rather becoming much more mainstream, the risk around data and the model security is very high. As a data scientist, you should know, as a data engineer, you should know that ensuring the data set security and privacy is very integral for your model development and deployment. So it must be a key consideration whenever you're doing AI application architecture review or testing or any of the development. There are limitations around model training time, inference time, and performance matrices. So all of that gets aggregated and integrated as part of your federated learning identity, because you might have to follow regulations like GDPR or CCPA, and it's an important part of your AI journey to have them. Now, federated learning, all of the things we talked about, is the machine learning on decentralized data. We look at the code, we look at some of the leading examples, and data is transformed or hashed or processed in multiple different areas. Doesn't mean you cannot do machine learning on it. It actually makes it easier to make your data public and publish it. And you can have an audit trail for this data, and you have explainability for those models. And it also creates opportunities for people to be able to create data ecosystems. Right? So federated learning is essentially that. This is a set of references here, so you can. I'll share these deck with the I've already shared it with the ACM, so you guys can take a look at it. There's a really good comic Google has created called g.co/federated. You can see it over there. Here's some of my contact information. I'll stop now. If there's any questions, comments, concerns, please let me know.
Since this is the most relevantly new field, it is coined by Google in 2016. What is the most burning question you see in federated learning? And if someone wants to do his doctorate degree in federated learning, what the area should be explored?
Okay, so the question is, this has been going on for a while, and what is the most burning question in this? So yes, federated learning has been around for a while, but so is machine learning, right? The logistic regression has been around since 70s. Federated learning, what are the different things you can do for federated learning in real world? That is the burning question. So right now people are doing research and doing their PhD dissertations on differential privacy, figuring out what kind of differential privacy guarantees you can still have while still being able to explain your data set. So explainability, if you look at the research around explainability, it has skyrocketed. There's a lot of publications happening around interpretability, bias around data sets. So one of the good areas for research could be, if you are applying federated learning, what happens to the data bias? What happens to the model bias? How does it manifest itself in federated learning environment? And what can you do to reduce it? I think that will be a great area of research people can work on to figure out how the bias manifests itself. The second could be interpretability in federated learning, how you can interpret the results based on that to ensure that there is no decay happening, or accuracy and precision and recall and other attributes of your model are not getting compromised. And what are the fine tuning of automated machine learning can happen in this case, where you are training a model without having to do unnecessary work associated with the differential privacy of federated learning, which impacts your results for your interpretability of the model. So when auditors are looking at it, they don't they have some explanation as to why this model has changed, or what is the impact of differential privacy of federated learning on that model. Third area could be if you are building ecosystem as in you are asking a bunch of different banks to share their data, how you can make a framework which explains to those banks that when we are applying federated learning or differential privacy, their data is safe. They don't have to save the data. So I used to work with MIT on a project called OPAL, OPAL, and that project is now available publicly. It's called Trusted Learning. You can look it up. It's called Open Algorithms Project, OPAL. We did some open source development for that. So MIT has made it an individual entity now. You can see other things around that project. So if anybody is interested in working on Trust platform, shoot me an email. I'll point you to the right resources.
When we talk about explainability, this is kind of a different ball game right now because talking about federated learning. When we talk about explainability of AI, what is exactly that? Do we
I can't hear you hear your full question. I think you said about explainability and then you dropped off. I think the question was from Muhammad Hafiz. Explainability is a different ball game. Yeah, so explainability is more about how you will apply, like say, counterfactuals or Lime and Shapley values, or how you would use techniques such as perturbation and be able to get the results. How your model is a black box versus a white box model. How do you explain those models? So there's a bunch of things you can do to explain your model, and interpretability and explainability of model is of course a huge topic. But as part of the federated learning, because you are obfuscating the model in some way or form, how does that impact your global model? That's what I was talking about, and how it will be used as part of that that larger engagement. I hope that makes sense. I think the person who was asking question couldn't make it, but yeah.
Okay, so since we have so many compromises on data in federated learning that we have might have different applications, we might have different feature space and all that. So how do we term accuracy in federated learning? Is it the same way as we discuss it in traditional machine learning algorithms, or do we define it in some different way?
The accuracy, the matrices and the KPIs you have. So accuracy is one of the matrices you have, but there could be tons of other matrices which you use. So for example, I work a lot on NLP space, and the Roge matrix is a big matrix we use. The blue matrix is another one we use for MT, the machine translation. That's a great question. In order for aggregated algorithms, aggregated models to work in terms of federated learning, you don't necessarily need different matrix to be able to measure individual and the federated learning, because you are dealing with the models locally the same way you are going to be dealing with a model on the server. So locally, your accuracy, your precision, and recall is getting calculated over at your local scale, and you can essentially transfer those matrices over to the server to see how it works locally. But at the same time, the server's calculation or the aggregated model you have has its own matrices. Either it's a blue score, or if it's Rouge score, or it could be accuracy, it could be precision, it could be recall, it could be any other KPI you might be using. So it doesn't change, it stays the same. However, you would be able to see individual statistics, and those are the data sets, and that information is kept separate. So for example, if you want to find out if your Android devices are performing better than your iPhone devices are performing better, because there could be device independent results and matrices based on that. So the telemetry information is separate from the model result information. So the KPIs might be telemetry related, or it could be model related. The model related KPIs stay the same, but the telemetry related KPIs might differ based on the different devices or edge nodes, because the computational limitations are different across different devices. So you can't expect all the models to behave exactly the same. I know it's a little complex answer, but it's in real world implementation. Whenever I have implemented federated learning or differential privacy, the KPIs have to be very nuanced.
Okay. So one last question from my side. Apart from privacy, what practical problems do you think federated learning can solve that traditional machine learning algorithms cannot?
So federated learning is not a hype or something. It's practical, like it's used every day today for any consortium. So we work with a lot of healthcare consortiums, a lot of financial services consortiums, and then they are separate, sharing data. They are using federated learning. You are using federated learning right now with your phones. So your phones have all the implementation of federated learning for like several years now, and they are all the voice data you have, all the Gmail keyboard data you have, every time you type in an email, and it learns new words from it, all the Grammarlies of the world, all of that information gets aggregated through federated learning. So these are anytime a real world use case for you, anytime you are trying to share data, which is private, and it has IID, and it has individually identified information, you need to make sure that you're using federated learning, differential privacy, and either any protocol which ensures that your user's privacy is not getting compromised.
Okay, thank you. Thank you very much.
Of course, of course.
We are going to conclude today's session, sir, on behalf of the Department of Computer Science, GCU University Lahore, GCU-ACM Student Chapter, and Honorable Vice Chancellor at GCU University Lahore, Professor Dr. Masood Zaidi. We would like to thank you, sir, for joining us today and delivering an insightful, interactive, and engaging talk on federated learning. We would like to benefit more from your valuable experience and insight, and would like to have you with us for further future talks on trending technological areas. Thank you, sir.
Absolutely, it was my pleasure. Thank you very much. Assalamu alaikum.
Thank you.